So, in the last lecture we talked about graphical models, and we basically discussed how we can set them up with nodes and arcs between the nodes. We can express direct influences or through these conditional probabilities with like directed arcs, and each node represents a random variable. We talked about directed acyclic graphs, and we discussed a bunch of examples. In this case, like one of the simpler examples with just two random variables and like one arc between them that is directed. So there's a direct influence from rain to wet grass. Obviously, like it is one like more or less of a clear relationship that we know about, and it's kind of like as a little bit of a hint towards what we're talking about a little later. Is also obviously these relationships can be basically assumed through what we know. So for example, if you have some prior or top-down knowledge onto your data, you can come up with these graphs yourself and basically identify possible relationships through your data and retrieve or diagnose what's going on. So for example, if you observe that there is rain, you can infer from that quite clearly if there's going to be wet grass, but you can also turn this around by observing or diagnosing that there is wet grass. So like what could have been the cause? Obviously in this example, it's more or less a little bit trivial, but in more complex examples that we talked about, there are these relationships that are excitatory. So in this case, this would be an excitatory relationship. And there are other relationships that would be inhibitory, that would reduce the probability of the cause for wet grass, or basically would remove certain support for different causes like rain, sprinklers, and so on. All right. So we walked through a lot of these examples and tried to identify how we can compute the joint probability between rain and wet grass through just these three parameters, and the joint probability can be expressed as such, and this is a lot more easy for us to visualize or to understand in form of a visual representation rather than just like writing it like that. So this is one of the reasons why we want to use these graphs. We talked about the, so we went through all the examples, like, okay, so how do we compute the probability for wet grass? And so we need to compute the marginal probability over rain, and basically come up with this, so we have to compute the marginal probability of the joint. With rain, and so we have to compute this for rain and no rain, and we know all these variables here from this table, so we can compute that very easily. Then we talked about how we can turn this around. So like when we observe wet grass, we can walk backwards in this graph as well, and now we kind of increase the probability that there is actually rain. So from the general probability of that, if we don't know about the wet grass, we know that it rains with 40% probability, or 0.4 probability. But if we observe that there is wet grass, that actually increases. So that's kind of like what I mentioned before when we have these positive relationships, or these excitatory relationships between two random variables. We talked about how we define independence between variables and conditionally independence. So this can then be expressed through different types of graphs. So for example, there is no direct relationship or no like directed arc between x and z, obviously in this way to write it, okay? We talked about the canonical cases of these more complex graphs with three variables or more. So we had this head to tail connection. It's kind of like forming this chain. Our example, was the following. And then based off of these 5 variables, we could also, again, express the entire joint distribution, which in this case is like computed by these 3 terms here. So you have P of x, there's no direct relationship to this one, so that's P of cloudy, P of y given x, this is cloudy given rain, so rain is y, and z is wet grass, and that's with given y, so there's no direct connection from cloudy to wet grass, for example, right there. Okay? Then we can compute those guys. Basically, in this case, P of r, we don't need to go in this direction and compute the marginal over wet grass, but we compute the marginal over the cloudy parts, and we can basically compute this local, these local probabilities without regarding wet grass to compute the probability of rain without observing wet grass or cloudy at this point, and the same for wet grass. And for wet grass, we don't need to go all the way up here, because in this marginal we kind of observe the rain either as yes or no, so we don't have to move up all the way. So these are independent through knowing what rain is. Yeah. All right. And then we can also go all the way up, or all the way down in this case, from cloudy to wet grass, but also from down from the wet grass all the way up to cloudy. And we do this through the Bayes rule. Okay, then we talked about this tail-to-tail connection. In this case, the joint density is computed through these 3 terms here. Our example again with the sprinklers and rain and cloudy, and again through these 5 variables we can compute the entire joint distribution. And I think the main idea is to like kind of play around and try out a couple of things with these graphs and try to compute some probabilities yourself at home. Yeah, and so for example, in this case, if we observe that there is rain, that in general increases the probability that it is cloudy through this excitatory relationship. If we observe that there is a sprinkler, that actually would reduce the probability of having the weather to be cloudy. Okay, so there's these different types of relationships. Yeah, don't want to go through all of these examples, but I think you get the. Well, I guess this one was important through the to see the other way around, so that it actually can reduce the probability. We have these head-to-head connections as well. In this case, we have 2 variables that are completely independent of other variables x and y, but then we have one variable z that is dependent on 2 variables. Okay, and again through these variables we can express all the possible probabilities that we want to know within this distribution that's represented by this graph, such as the P of W. So what's the probability of wet grass? Now we have to compute the marginal over 2 variables, because this one is dependent on 2 variables. And as you might imagine, well, we have to go through all the possible expressions of these. So it could be rainy and sprinkler on, rain and not sprinkler, and so on. Okay, so that's why this is like 1, 2, 3, 4 terms in this case. Okay. Hey. All right. And then we can compute all these other variables as well. And in this case, another important aspect was explained through this called explaining away. So if we actually observe both rain and wet grass. In this case, the probability of sprinklers is going to go down because we observe two variables that then kind of reduce the probability for sprinkler, while if we don't know that rain is present, we kind of associate, or could associate, the wet grass with the sprinkler instead. So that's kind of like, so in a case where we only observe the outcome, which is the wet grass, the probability of having the sprinkler on could be quite high, because there are these relationships here with the sprinkler on and these two here, where there's very strong evidence that if the sprinkler is on, that there's going to be wet grass. However, if we know that rain is present, we kind of explain away, or kind of like reduce the probability of having a sprinkler on, because we now kind of know one of the causes that could be associated with that. All right. Yeah, and obviously if we know that the sprinkler is not, or that there's no rain, then obviously that will go up again, because then we have still the observation present, which is the wet grass, but we do not know the evidence yet, or we know that it did not rain, so like the probability that it actually is a sprinkler is increased. All right. Then we mentioned that we can also actually move on to create these more complex graphs. In this case we have 4 variables, and now we need a bunch of more variables to actually express the entire distribution, or the entire density, and we can compute still like, for example, connections between wet grass and cloudy, so we can walk over the rain as well as the sprinkler in this case to understand what the relationship between cloudy and wet grass are. And we could also go, obviously, the other way around, from cloudy down to wet grass over sprinkler and rain. All right. Very good. So in general, we can write basically, so this is the joint distribution, or joint density for the 4 variable example, where cloudy doesn't have any parents, sprinkler has cloudy as a parent, rain has cloudy as a parent, but wet grass has both sprinklers and rain as parents. In general, we can write the joint distribution as the following product, which basically has the variables given the parents, or like, and that can be variably many parents. And so you can easily describe or derive these joint densities from a graph if you like number these through A, B, C, D, E, F, and then you basically just compute these local ones, and the global density is the product of just all of these local ones. Okay, and so computing those local ones might actually be a little easier than computing the global probability all the time. Obviously, there could also be hidden variables that we do not observe. I gave one example here where, for example, a person buys milk, baby food, and diapers. Well, obviously there might be a baby at home, but we don't know that, we don't observe that, but it could be like a hidden variable that causes this person to purchase these items. And obviously also, like, for example, if we observe cloudy weather, well, there's other hidden variables in play, such as like humidity in the air, like temperature, and so on. Okay. And we could, however, also basically fill in the probabilities for these hidden nodes if we wanted to, so we can add those nodes in those graphs as well, and infer the probabilities for those hidden nodes provided our data if we wanted to. Okay? And also, like, a note of caution, so to say, is like that these connections between nodes does not always indicate causality, but rather a direct influence, or like kind of like a correlation. We can use these graphs not only for like basically representing densities, but also for classification, and the classification models that use these type of graphs for classification are so-called generative models. So, and we're gonna, I think we have talked about one generative model, which is the naive Bayes model, but also, so we're gonna talk next week about hidden Markov models. Those are generative as well. And we have, I think, talked about the other form of models quite extensively, which are discriminative models that try to identify a decision boundary rather than like model the distributions or the densities for the certain classes, where then you can classify based off of like the posterior probabilities rather than like am I on the right or the left side of the decision hyperplane. So discriminative models, for example, are support vector machines, conditional random fields, and so on. Neural networks, you could imagine, are discriminative models as well, even though some people like kind of use them as generative models right now sometimes as well. All right, so for classification, again, like we basically want to compute the posterior probability for a certain class given a certain observation, and well, it's kind of like very similar to this evidence kind of, or this diagnosis problem that we mentioned earlier, where we observe wet grass and we want to know what the cause of that is. Is it rain? Is it cloudy weather? And so on. And so basically, through the Bayes rule again, we can turn this kind of like this term around, and now have basically the likelihood here, the prior probability of like a certain class in the first case, and then the evidence of observing the item at all, or the observation at all, which, if you have multiple classes and you need to compute this, obviously we talked about this before, you could, for example, actually remove that in that case. Since we can use generative models like naive Bayes, etc., or they can be seen as these kind of graphical models, we can also represent them as graphs, right? And so one example here would be, for example, this one, where we have the random variable C for the class itself, and then a random variable for the observations. And in this case, we have a direct relationship between the class and the observations, which is something that we would hope is present in our data. So we can express p of x through this p of x given z, and p of c in this case, and in this, like for this representation here, x is multi-dimensional, multivariate, while in a naive Bayes classification problem, you would split up this observation vector into like independent nodes. So that's kind of like how you kind of represent the independence between the single dimensions of your observation. So like all of these are completely independent from each other given a certain class C. And that obviously is also sometimes a correct assumption, but sometimes also not. And naive Bayes, I think, is most popular used in like text classification, where you have like bag of words, and yes, you can assume that each word in your vocabulary is independent from the other words, but that's obviously not the case, right? Like you're using, you have a topic in mind, and that topic like kind of restricts you to a certain type of vocabulary. You have a certain context, like are you writing to a friend, are you writing to a boss, etc. So like the choice of words is not independent from each other. However, it kind of works well enough for these classifications. Okay, so that's kind of like how you would represent a classifier in such a case. Okay. All right. So now I would like to talk a little bit more before we go into like more complex models, and we're not going to go too much into detail for that. But I'd like to talk about d-separation, which is basically the direction-dependent separation between nodes, and a simple way to identify within a graph or a graphical model, like what variables are independent from each other, is the so-called baseball kind of game. And these are the 6 rules that you have to kind of keep in mind or need to follow in order to identify if a certain variable with another variable is independent from each other. Does anybody know what the white ones versus the gray ones mean? So the white ones are variables that we do not observe, and the gray ones are variables that we observe in this moment. So these are kind of like part of the evidence that we have, and that's kind of like one of the ways you can represent graphical models. So for example, here, if you wanted to think about this model here, because we will never, in a supervised learning problem, will never really observe in like our generalization or in the actual runtime, except outside of training, is what I mean. We would never observe the class itself, but we always observe this, so we could kind of like visualize this observation as gray and that one as white, so that we know, okay, so we are observing this part of the graph, but we're not observing that part. So that's kind of like inferring kind of like a hidden variable from it, okay? Yeah, so I can use these rules to check which variables are dependent or independent from each other. I brought 2 examples. So if we observe this z variable here, we wanted to know if x and y are independent from each other. We need to try to follow these rules. So first of all, we start off in this x graph here. So this x has only an arrow coming in, right? So that means it's kind of like this node here. So it has only arrows coming in, so we can choose to go only against that direction. So we have to kind of like turn around here, right? So we turn around in this direction, or we turn around in that direction. And so we walk up this graph here. And so now we are ending up at this one, which is kind of like this one. So we can choose to either go this way or that way, or like basically down here. From this graph, we also have kind of like two arrows out here, so we can also walk down this way. And so this guy is this kind of graph, and then we walk up to this one here, which is a observed variable that has 2 outgoing arrows, so we have to turn around, so that we can't go further than this, we can't go past that node here, okay? So we have to turn around in that case, and then so we come down to here. This one is one that has multiple ins or a chain again, so it's either this one or actually this guy here. And so in the case of like trying to go up here, we have to use this version of the graph, so we can't go up there. And if we consider it to be that one, we have only one option to follow the direction that we came from, so we have to go down here. This one again is only a graph that has incoming directions, so it's one of these, so we have to turn around and we are blocked again. So given z, x and y are independent from each other. Okay, so that's kind of like how you can denote that, okay? So x and y are independent given z. And so now the trick in this case now could be, so what if we also observe w, okay? And if we observe w, well, this node here, which was that guy, now becomes that guy, right? So, so now we can actually move in the opposite direction as well, and then end up at this node, which is allowing us to go in. So this basically is becoming that guy because we followed this path. Then we come up here and are able to choose this path now, and and can just walk up to the y. So now they are not independent anymore given our variable w, okay? So that's kind of like the idea of these.
From that graph, like, can you explain again how to tell like x and y are not independent?
What?
Based on that graph, how do you tell x and y are not independent?
So that's like basically you have to again start off from this node, and we talked about this until here, so we can and we can then we talked about that with these rules we can walk into that one, but now this guy is actually observed, so now we have to not use this version of it but this version of it. So in this one like bounces it in the other direction, but in this case we can walk in the other direction. So we come in one direction, walk up the other direction, and now end up in this graph here, or in this node, which in our case now is this guy, but with the arrows in the other direction. So we don't come in from this side, but we come in from that side, and this allows us to just go past it into the y node.
Sorry, what do you mean like by passing it? Like,
well, it's like this is just a visual representation of like what these densities like allow you to do. So what you want to, like, for example, sometimes compute is like so in this case, like, what is the probability of x given z, right? And in this case, to be able to do that, well, you have to compute the probabilities of certain other nodes as well, right? And you don't necessarily want to compute it for all the nodes, right? But and so you don't want to, for example, compute what the probabilities for y are, okay? But if they are dependent, you can't just ignore that, okay? So this allows you to basically reduce the computation that you have to do. If you know that they are separate or like they are independent from each other, if you want to observe the one or the other, well, then you just can leave that out if they're independent from each other, right? But if they're not independent from each other, you have to compute all the possible ways there. So that kind of like increases your computational needs. So it's like just a basically like a way to reduce the computational need and also to kind of understand the dependencies among the variables. Does it make sense? Okay, very good. So, and in general, this basically can can be reduced to belief propagation, and like if we want to expand our graphs to like variably large graphical models, we can use belief propagation to compute support for, or like the probability of certain variables. And yeah, so we want to have an algorithm that basically generalizes to all of them. And to generalize the tail-to-tail connection, or the head-to-tail connection, we can, for example, consider them to be chains. And basically what we have to do in chains is, if we want to know the probability of x, well, there is some evidence somewhere up the chain, and there is some evidence somewhere down the chain. And that could be nothing, right? Like if there is no evidence down the chain, well, then they're independent, so I don't have to compute all of this stuff here, right? But if there is evidence down the chain, well, then I have to propagate the evidence back up the chain to x, and then I have to also propagate the evidence that I have from up the chain down to x. However, for x, or like x then, however, stops this, and I don't have to propagate the belief or the evidence from down here all the way up here because x stops that. Okay, so that's kind of like one way to see that as well. So you don't have to compute all the way up here for this part of the evidence, and neither from this part of the evidence all the way down to there. So basically, you can split it up into two parts, like where you have evidence down the chain and evidence up the chain. Okay, it's just kind of like a general representation. I don't want to go into too much detail here, but and then if you want to kind of expand that further to the example of trees, where each node has only one parent but multiple children possibly, then you have to again propagate all the information from or the evidence that is down in the child nodes all the way to the node that you want to compute, as well as from the parent node that comes down. And so if we wanted to understand what the probability of x is, well, we have to propagate up the information from all the child nodes, and then up also to the parent node of this node that we have, but then also from the upper the parent node down to x, and then again, because x has dependence as well, down to the children as well. So this kind of like just makes it a bit more complicated. And in this case, you have the evidence somewhere up in the upper part of the tree, so the E plus, and the evidence minus is somewhere down here, and you can split that up basically into this probability, and you split it up again and separate this out. For polytrees, they can have multiple parents and multiple children, and again, you have to kind of like split this up and walk through all the parents' evidences as well. So this is kind of like just getting more and more complex and more complicated. But in theory, if you're not working with like super complex graphical models, you don't really encounter these kind of issues. All right. So one of the things that you could also ask yourself is like, how do we come up with these graphical models in the first place? Like how do we know that the graphical model that we have is the right one to use? And well, in general, that is actually really difficult to do, and you could imagine to basically kind of like iteratively grow your network, or you could actually ask like experts to give you some top-down knowledge so that you understand better what their expertise is. Like you know, for example, medical doctors have a lot of like top-down information. If you ask them about like the relationship between certain blood factors or something, like you better understand the relationship between certain factors in the blood that like cause, for example, like the blood to clog, or what happens if this variable is not present. So well, okay, that causes the blood to not clog, and that is an issue, and so on. So like you kind of want to often use this kind of top-down or expert knowledge to come up with these models, because in general, to derive them from the data itself is not very easy, because you don't necessarily know that you observe all the variables. There might be hidden variables, but which ones are they? Like, where are they? What do they influence? Is there, for every observation that you make, is there a couple of hidden variables, or is there just one, and so on? So this is kind of like complex to do. So what you want to actually come up with is basically derive a graphical model from expert knowledge, and then basically identify the relationships between the data through that. Okay, so just to finalize, or to summarize why graphical models are interesting, Well, on one hand, they can easily visualize dependencies among variables and allow for more intuitive and better understanding of the relationships. And we can efficiently compute inference, like what is the probability of a certain variable given some evidence, but you also can kind of use it the other way around. Can use it for prediction, but also for diagnosis of like what has caused a certain observation. This is kind of like the neat ideas about graphical models. Are there any questions? Right, so we can take like a 5-minute break and come back. Or, yeah, 5-minute break, 10:45, and then talk about user studies.